cover the topic on time-dependent transport. Okay, so there are actually 3 sections for our lecture that we are going to discuss today, right? So when we talk about time dependent, so which means we are going to deal with unsteady state process. Okay, unsteady state process. So for this topic, right, so here is where we are now. All right, so now it's week 10, right? We are going to cover the time dependent transport, and then this is what we are going to do on week 11. We are going to cover on the boundary layer theory, focusing on the velocity boundary layer theory first, right, on week 11. So week 12, it will be a guest lecture by Associate Prof. Dr. Salim, all right, guest lecture. Okay, and then take note that it will be replaced on Tuesday because Monday again is a public holiday, and then the test is on Thursday. Okay, so I'll brief you about the scope of the test later, all right, towards the end of the class. And then on week 13, we'll then continue with another part of the boundary layer theory topic. So we are going to focus on the thermal boundary layer. Right, that will be week 13. So then lastly on week 14, then that's our revision class. Okay, so that's the plan for the next few weeks. Okay, so now just to remind everyone where you are now. So okay, let's have a look at the MI. Okay, the assessment schedule. So if you see any of your friends joining the session, please help to admit them into the session. Yeah, thank you. Now, so far, all right, so for this module, right, so we have done the first the assignment one, right, that you have submitted last now it's week 10, right? So you submit on the end of the week 7, all right? Then, yeah, I'll try to finish the marking by this week so that at least you can receive the feedback to have a look at how you can further improve for your assignment 2, right? So I'll try to finish it latest by Friday morning. I'll try my best. Okay, then for assignment 2, that will due on, suppose week 9, so it's extend to week 10. So please complete it as soon as possible. So 11:59 p.m. in case if anyone missed last week class, right, or missed the announcement. So assignment 2 will due on this week, Friday, 11:59 p.m. So as for your test, it's on week 12, right? So we'll only cover learning outcome number 3. So I'll brief you about this towards the end of the class. So practical, we have completed all the lab session. Just a reminder, so for the submission, you just follow the your lab timetable. Right, so even if you finish in advance, so I'll allow you to just do the submission according to your timetable. So even for your submission date, follow the one in the timetable as well. Yeah. All right. So for final exam, we will cover all your 3 learning outcomes. So no worries, we will have revision class, and then I will discuss with you some of the final exam level past year question. Right, so that you have an idea what's the scope and how it is like. Okay, so this is our assessment plan, yeah, just to remind everyone, just in case you have forgotten about it. All right, so for today, there are 3 parts for our lecture. So the first part will cover about time-dependent flow, so which means unsteady state flow. Right, and we are going to focus only on the Newtonian fluids. All right, for the case, let's say if we have a plate and then you have a fluid that is suddenly being set in motion. If we move this plate here in X direction, right? So you are going to look at how the velocity profile actually changed with position and also with time, right? So your Vx now is a function of both y and t. So previously what you learned is if it's for steady state, right, your velocity profile is only a function of y. It will not change with time, right? So that's the difference between when we discuss about time-dependent flow and the steady state momentum transfer, yeah? Okay, so then we'll look at one example also later, and how we solve all this, no worries. All right, so for all the for the first 2 parts that I will discuss with you, all right, so this 2, how we solve it is by graphical method. All right, so we will solve using graphical method, and but I'll still need to cover the theoretical part with you. All right, so I'll go through some of the theoretical part, like how the equation is being formulated, and then to the part that they convert all the solution into a chart, which we can use conveniently. So for the formulation part for this topic, right? So no worries, you're not expected to know how to do that, right? Because we can't actually solve it at this level. Okay, so that's why for this topic, the learning outcome, right, it will map to only these two learning outcomes. So for the time-dependent flow, then is related to the analyze the flow behavior of engineering system using the laws of conservation, right? So it will map to the analyze level only, not the formulate, right? No worries. So then the second part of our lecture today, we'll discuss about unsteady state heat transfer, right? This is something that we have never discussed before, right? So most of the time you might know that the flow might not be, it will not be steady, but how about heat transfer, right? So heat transfer, there are some cases where it will encounter unsteady state heat transfer as well. And then same thing, we'll use graphical chart to solve for unsteady state heat transfer. So this one will then map to your second learning outcome, analyze the thermal behavior of engineering system using the laws of conservation. Okay, and to the final part, right, this is something interesting. So like mass transfer, last time for unsteady state mass transfer, you all learn about the numerical methods where you need to derive the equation for each of the nodes, right? And then you do a calculation by iteration method, what would be the equilibrium concentration on it. So this one here, it's slightly similar concept, but we can actually solve it directly by hand calculation. No iteration is required actually. We can solve it by hand calculation. And the same concept is such that we will assign nodes into the system also. And then there are formulas that are ready. Then you just need to apply it directly to the nodes. Then you can do the calculation. Okay, so that's the last part that we are going to discuss. All right, so 3 sections today. Now, so why do we need to learn about time-dependent flow or say state flow process? Because we know that usually when you start up anything, any process, right, even when you open your tap water, you notice that the water that is flow out, right, it's not in streamline manner first, right? Usually it's something like burst out first. So definitely for the start of the process, a few seconds or 2 minutes, right, there will be unsteady state flow. All right, and when that's the case, then usually the velocity, it will depends on the position and time. So let's say if it's a flow in the x direction, all right, so okay, let's say this is the x direction, this is the y direction, all right, so your velocity, if we know that it will then vary in y direction, right, because at the surface, all right, so let's say this is the case where you are going to set this plate here in motion, and then by applying a force, and then the plate will set in motion at a velocity of v naught. Let's say at a velocity of v naught. Then, right, at position y equals to 0, the velocity x will be equals to v naught, right? All right, suppose it's that, and we know that when it's sufficiently far here, so let's say somewhere here, okay, so y equals to delta, our vx, it will almost approach 0, right? Because this is the case, all right, don't confuse that. This is the case if we set this bottom plate in motion, okay, in motion. So definitely your velocity in x direction, it will vary with the position already. So when we deal with time-dependent flow, all right, so for time-dependent flow, then your velocity in x direction is also affected by the time, right? So from time to time, your velocity profile, it might be of a slightly different shape, right? It may still have the curve shape, but it might be slightly different, okay? So now, because now your velocity varies with y and the time, right? The position and the time. So later you'll notice that the equation of motion that we are going to solve, right? Uh, uh, we are not going to solve it, okay? That as they derive, all right? So you'll notice that is expressed in partial derivative form, right? So you have maybe secondary x respect to y, something like this, right? It will be in there is some other terms here, so it will be expressed in partial derivative because your vx varied with time and position. Okay, and to solve such equation, right? So this would be then the mu over density. All right, so to solve this equation here, there are a few methods that you can see here. We have the method of combination of variables, separation of variables, and the method of sinusoidal response. So we are not going to discuss this one because for the method of sinusoidal response, right, it it will only applies to some cases that deal with maybe if we have the system that is responding to some external forces in periodic manner. Right, so then so that's why we are not going to discuss this. So this method here that I mentioned just now, the combination of variable methods and separation of variable methods, right? So we'll be introduced to it, right? So I'll show you, right? So the introductory part, how they actually come to the solution, right? So for time dependent flow, right? So for time-dependent flow, there will be an example which how they are going to solve it using the combination of variables. Then the separation of variables, right? You have an example later how they apply it to time-dependent heat transfer. Okay. Yeah. So let's see if it's the case here. All right. So you have a plate here. Okay, there's a plate here, and you imagine, all right, there's a layer of fluid, right? And then at some time smaller than 0, the fluid is still at rest, right? So this is position X, all right, and the thickness of the fluid or the film of fluid is in Y position, right? So at time equals to 0, but if the fluid is at rest, then which means the Vx is equals to 0. Okay, so let's say you assume that this is a very thick layer of fluid. Okay, that's very thick layer of fluid. Okay, and this one semi-infinite body of liquid. Okay, then let's say now at time equals to 0, this bottom plate here, this one, you apply a force, let's say Fx. Okay, and then it will set the bottom plate in motion such that this plate here, it will move at a velocity v0. Okay, so in that case, which means at some time, right, slightly larger than 0. Okay, so we will know that here, as what I mentioned just now, when y is equals to 0, right, so no slip condition, then the Vx, right, at y equals to 0, it will then travel at the same velocity of the bottom plate, right, while at a distance sufficiently far away from the plate y equals to delta, the Vx is equals to 0. Now, for this case, right, let's say this is a very thick semi-infinite layer of liquid, right? It's a very thick liquid. So at a very small time after 0, all right, so your velocity profile might looks like this. Okay, but then after some further time, right, so then your velocity profile, it may travel like this and then goes on like this. So that's why what we mentioned just now, right, when it's time-dependent flow, the velocity in x direction, it will change with the position and the time as well. Okay, all right. So now, so let's see how they are going to simplify the equation of motion. Okay, so so we have talked about this just now, right? So this is only flow is only in x direction. So if that's the case, we know that velocity in y of the fluid and velocity in z for the fluid, it will be 0. So if Vy and Vz is equal to 0, so you recall back, this is the equation of motion, right? This is equation of motion, and this is the continuity equation. Okay, the continuity equation for Cartesian coordinate. All right, so if Vy and Vz is equal to 0, which means the first derivative of Vy and the first derivative of Vz would be 0 as well, right? So for the continuity equation. So here, if partial derivative of Vx respect to x is 0, then the second partial derivative of Vx respect to x, it will also be equals to 0. Okay, so, okay, hold on. There should be no 2 here. Okay, so now that's how we simplified this term on the left-hand side as well, right? So this is from equation of continuity, and Vy and Vz is equal to 0 because flow is in x direction only. Okay, so at the same time, we do a quick revision for equation of continuity here. Now, for this one, the rate of change of velocity respect to time, right? So for this case here, because we are discussing the case of time-dependent flow, okay, so that's why we will need to retain this one. So we'll retain this because it's unsteady state process. Unless if it's a steady state process, then like what we did previously, we will assume this term here to be 0. Okay, so now then the second derivative of Vx from x is equals to 0, right? That we have proved it from equation of continuity. Okay, and the flow, all right, so the Vx, right, it will only varies in y direction. Vx only varies in y direction. Okay, so therefore we will assume this term to be 0. Okay, and as for raw gx, because it's a horizontal flow, right, so that's why we assume the raw gx to be equals to 0 as well. Now a bit of special thing for this case here, this one here, the pressure drop, right, the rate of change of the pressure respect to along, not to say the rate of change, is the change of the pressure along the length of the plate, right? So for this case here, it's equals to 0, even if it's for horizontal flow, because this change in pressure, right, it is equals to 0 because there's actually there's no we are not assuming if there's any fluid that actually push, that is behind, let's say this section here, that push it forward, but it's actually due to this plate that is set in motion that cause the fluid to flow, right? So that's why this term here, it will be equals to 0, right? So now with this, you can see that the whole equation, uh, okay, it will then reduce to partial derivative of Vx respect to time is equals to, so the viscosity, right, divided by the density. So you have this term on the left hand side, right? And then this term, okay, let me use another color. This term here, this one, and this one. Okay, so then okay, rewriting it. Okay, so now you can see, right, so the rate of change of Vx, velocity in x direction with respect to time, is equals to the viscosity divided by density, then multiplied to second derivative of Vx with respect to y, which, all right, so this term here, right, viscosity divided by density, we can also express it as the kinematic viscosity, right? So that's why this equation here, the equation of motion, it can then be eventually simplified to this form here, right? So the kinematic viscosity here is the viscosity divided by density. Okay, so your equation of motion will then, for Cartesian coordinates, flow in x direction, it will then be reduced to this form for the case of time-dependent flow, steady state flow. Now, so now this is a very special case, right, where you can see the Vx, okay, it varies with both time and position. So it's a partial derivative. Then how we can solve it? It's unlike what we did previously. All is then reduced to ordinary differential equation because your velocity is not changing with time, right? So then your velocity only varies with one variable. But this case here, it varies with two variables. Okay, so now how one of the solution, right, that proposed by a person called Blasius, all right, so you learn more in depth about this one, the solution that we discussed today actually on next week, right? So which is related to the boundary layer theory, right? So it's proposed by Blasius here. So for this solution that you are going to see, they are using the combined variable method, right, to solve it, and eventually all the solution, it will be presented in a chart form. Okay, so okay, now how actually they solve the partial derivative of this one here, right? So first you need to understand the boundary condition clearly. So we know that when it's at rest, right, just now, when t is smaller than 0, we know that all the velocity at any position, right, so throughout this whole layer here is equals to 0. Okay, but when the fluids here, the plate here is set in motion, so we know that y equals to 0. All right, so which is here, your velocity of the fluid at this layer here, it will travels with the plate velocity, and at y equals to, let's say, because it's a semi-infinite layer of fluid, right? So apologies, this one just now we should put it as infinity, right? So then our velocity at a position sufficiently far away from the plate, right, in the fluid, the velocity Vx, it will then be equals to 0. Okay, now then to solve this, all right, so for the combined variable methods, this Blasius here, it proposed a dimensionless velocity. Okay, so this dimensionless velocity is expressed as, this one you can call it as phi, all right, so let's say you can call it as phi, the Greek mathematical symbol. So it's expressed as Vx, so which means the velocity of x is in any position y and any time, right, with respect to V naught, right? Because you know that this is the maximum velocity of the fluid, right? So it's a maximum velocity of fluid. So this phi here is expressed as a fraction of the Vx with respect to the maximum velocity. Okay, so okay, let's continue. Yeah. There are only 12 students in the session. Do you all have any, are you all rushing any assignments or any tests this week? So if you see your friend is not here, right, please help to remind them to join the session. We have lecture today, 10 to 12. Okay, please remind them. Right, they will need to at least attend 1 hour for the attendance to be counted. All right, so it's 10:30 now, so please ask them to join as soon as possible. Okay, now let's continue. So this is the equation of motion that we have simplified just now, right? So the Blasius, when he proposed to solve it, we will try to, he used the combined variable methods to try to reduce this further. This is a partial differential equation, and he applied the phi just now, right, the Vx over V naught, so that we can convert this equation here to an ordinary differential equation. All right, so now, so if let's say if you substitute the phi here, right, for the Vx and here as well, okay, so the equation, it will then turn into this form, right? So the first partial derivative of phi in respect to time, it will then be equals to the kinematic viscosity multiplied the second derivative of the phi, right, respect to y. Now, but if you look at here, the phi, right, Vx over V naught is still a function of time, and also it still vary the time and position. So which means you need another dimensionless number, all right, in order to change this one, so that this one, the change in velocity here, which is expressed in phi, can express with respect to just one variable. And to do that, right, so Blasius, he suggested, he had tried several combinations, and eventually he proposed this one. So this symbol here is called eta, all right? So he proposed that we are going to use combined variables. So this is the term just now, the method of combined variables. So he suggests, all right, a dimensionless combined variable, all right? So eta is equals to y divided by the square root of 4 multiplied to kinematic viscosity and time. All right, this is the kinematic viscosity. Kinematic viscosity. Okay, so now if we have introduced this, which means then, right, so we'll need to think of a way to re-express this, okay, here, this two things, right? So to do that, so first, let's solve for the first partial derivative of phi respect to the time first, right? So to solve that first partial derivative of phi respect to time, because your phi, right, so you look at here, the phi, right, so we know that it's equal to Vx over V naught, and it's also a function of eta, all right? So if you look at eta is a function of y and it's a function of time, right? So if we are going to take partial derivative of phi respect to time, right? Okay, but it's also a function of eta, then you need to apply the chain rule. Okay, you need to apply a chain rule such that you need to take partial derivative of the phi respect to eta first, and then multiply to the partial derivative of eta respect to time. Okay, so now let's try this. All right, so to get the expression for partial derivative of eta respect to time, okay, so okay, if we, okay, let's say let me rearrange this first. Okay, your eta, okay, let's say I express it in this form so that it's easier for me to do the differentiation. All right, so when it's divided, when y is divided by square root of 4 multiplied to kinematic viscosity and time, right? So you can actually re-express it as to the power of negative half. Okay, so then if we take partial derivative of eta with respect to time, okay, so then this will be equals to negative half of y, okay, and then so let me see, I better write it like this, okay, and then as for the time, right, so it will become negative to the power of negative 3 over 2, right? Okay, to the power of negative 3 over 2. Now, if we rewrite this one, it can also express as time to the power of negative half multiplied to time to the power of negative 1, right? Okay, so, and this section here, you'll notice that it's the same as this one. Okay, so which means we can actually, okay, so I'll show you if we rewrite it, it will appear like this. Okay, then divided by t. All right, so which means you can simplify it as negative half of eta per time. Okay, now then substituting here back, okay, so which means on this side our answer, it will then be negative half of eta divided by time multiplied to the first this one, the first derivative of 5 respect to eta. Okay, so this is how they obtain this answer here. Okay, so if you want to, you can do a screenshot, but actually you will not be tested on this. Okay, so no worries, it's for your, just for your knowledge. All right, but some of this skill here you also apply it actually to next week when we cover about the boundary layer theory. Okay, so we'll also cover it on next week. Now, so then, okay, so the next part here, right? So it's the same as what we did for this one just now here, okay? Because your phi is a function of eta and eta is a function of y, right? So that's why you can see we apply the chain rule, okay? Then for this term here, right? So you differentiate the eta respect to y. So which means it's only this part here. So that's why you get 1 over square root of 4 kinematic viscosity multiplied to time, right? So this is quite straightforward for this one. This should be fine, all right? But how are we going to get the second derivative of the phi respect to y? Now, then you can do it step by step, okay? So it's actually what happens, right? When it's a second derivative of phi respect to y, you are actually taking partial derivative, all right? So if we apply the chain rule, so it will look like this, right? For the first derivative, okay, eta respect to y. And when it's second partial derivative, which means you are taking partial derivative of this, okay, respect to y. Okay, now, however here, right, this eta here is also a function of y, right? So you need to apply second level of chain rule again. Okay, so it will appear like this when we solve it. Okay, and then partial derivative for eta respect to y. Okay, now then simplifying this one, all right, so we will get, let's see it, we'll get second partial derivative of phi respect to eta. Then you can see you have two of this term, right? So multiplied to partial derivative of eta respect to y square. All right, and that's why when we solve it, then it's second partial derivative of phi respect to eta, then this one, so it's the square, okay, if you look at here, this one, here is the square or partial derivative of eta respect to y, right? Which is this part here that you have solved. All right, so if we square it, which means here it will just leave with 1 over 4 multiplied to kinematic viscosity and time. Okay, all right, so this is how they obtain the solution. All right. Okay, no worries, everyone. This is just for your knowledge, right? You are not expected to do this, okay, for this topic. Okay, so with all this expression just now that they have solved, right? So you can see for this is for this one, all right? So and then this one here, we'll need to substitute it here, okay, in the equation of motion that we have simplified. So substituting it and rearranging it, so you can, if you want to, right, maybe I can show you just very quickly here. So you can see if we on the left hand side, all right, so substituting it, and then on the right hand side you have kinematic viscosity, all right, multiplied to this term here, so second derivative of phi respect to eta, then 1 over 4 this. Okay, now then simplifying this one, right? So let's see, this one it will cancel out, all right, and then we have, where else, let me see, we have time here, right? So time here, it can cancel out each other as well. Okay, and then so rearranging it, let's see. So did we miss anything? Okay, yeah, so if you rearrange it, okay, let me do it slowly. Okay, first derivative of phi respect to eta, all right, so then here it will be let's see, I think it's easier if we do it like this actually. So this 4 here, if I'm going to multiply here, so what we'll get is negative 2 eta, right? And then here we left with second derivative of phi respect to eta. So rearranging this, which means the second derivative of phi respect to eta plus 2 eta, right, multiplied to first derivative of phi respect to eta is equals to 0. Okay, so this is the equation of motion, all right, that is being rewritten in the dimensionless combined variable phi, right, and also eta. All right, so which means then for all the boundary condition, it has to be rewrite in eta and phi as well. So what it means here, so if you recall back, all right, so eta is equals to y divided by square root of 4 multiplied to kinematic viscosity and time, right? So here, which means at the position, right? So at initial condition, right? So when time is equals to 0, right? So when time is equals to 0 and y is equals to 0, so you can imagine you substitute 0 and 0 here, the eta will be equals to 0. And the phi is actually equals to Vx over V naught, right? And since, okay, here at boundary condition, oh, hold on now, let me see here. Boundary condition 1. Oh, I'm so sorry. This one, boundary condition 1 here, it actually refers to, okay, let's say at some time greater than 0, okay? But at position y equals to, yes, it's at position y equals to 0, okay? So if this value here goes to 0, okay, so your eta is 0, right? But if you recall back just now, right, the plate, if you set it in motion at v naught, okay, so the velocity profile looks something like this. At y equals to 0, your Vx will then be equals to V naught. All right, so here it will be equals to V naught over V naught, and that's why we get the value 1 here for the first boundary condition. All right, so then for boundary condition number 2, which is, let's say, somewhere sufficiently far away in the semi-infinite fluid, right? So that's when, okay, for the time bigger than 0 and at a position which is almost equals to infinity, very far away from the surface. All right, so if that's the case, which means, so you just imagine now your eta, right? Okay, which is this equation here, and then this value here, it almost approach infinity. So which means your eta would be a very great value. And we know that at somewhere here, right, when y is approaching infinity, so the Vx is equals to 0, right? So your phi, which is equals to Vx over V naught, is then equals to 0 over V naught, and that's why the phi is equals to 0. So all the boundary condition, it has to be rewritten in dimensionless variable as well. Okay, so with this, with the dimensionless boundary condition in dimensionless variable, and with this equation here, all right, so okay, not confuse you further. So how they solve this equation here, oops, sorry, so how they solve this equation now, for this part, all right, they propose that, okay, so they propose that the solution to the first derivative of phi with respect to eta to be equal to psi. Okay, this we call it psi, and the psi, right, is equals to this expression here. So there's actually a method to obtain this value, but I think I will not confuse you further today. All right, but if you are interested to know it, all right, you can also check with me how they actually come up with this expression here. All right, so if they postulate. All right, so the Blasius, right, he postulates that the first derivative of phi with respect to eta is equals to psi, and the psi here is the answer, right, is equals to a C1, all right, a coefficient, and then it's actually exponential, right, exponential of negative eta square. Okay, so if now for this, if first derivative of phi respect to eta is equals to psi, this psi here, right, and then if they need to get an answer for this phi here, right, then they will need to integrate the psi respect to eta. Right, so that's why, okay, so if they solve the integration, okay, so it's actually something like this one. They are showing, okay, so the psi is this expression here. So substituting it, okay, so it will be exponential of negative eta square respect to eta plus c. Okay, something like this if they solve the integration. So then yeah, if you apply the boundary condition here and then we solve it further, so this is the solution that they obtained. Okay, so which can actually be simplified into just, so what happens here? So what happens here is the phi, right? Okay, the phi, which is actually Vx over V naught, right? And it's a function of eta, all right? So it will be equals to 1 minus the error function of eta. Okay, so like this. Okay, phi is equals to 1 minus the error function of eta. Okay, so now, so with this, okay, so they just replace back the phi here, all right? So it's Vx over V naught is equals to 1 minus error function of eta, right? Where eta is equals to this expression here, okay? Or we can also rewrite it as the complementary error function of eta, okay? So then Blasius, he solved it for the case where we have the bottom plate here that is being set in motion, and all the solution is then compiled in this chart here. Okay, so that's why I say no need worry. For time-dependent flow, we are going to use this graphical chart here to solve for the calculation part. Right, so this one is for the velocity profile in a dimensionless form for flow that is suddenly set in motion. So it's being, this chart here is Vx over V naught. So this is the phi, right? And then here is eta. Okay, so let me see. Okay, now, so now, Blasius, he also found that, right? So when eta is equals to 2, right? So the Vx over V naught is equals to 0.01, right? So which means, right, Vx is equals only to 0.01 of V naught when eta is equals to 2. So which is actually not shown here, right? So let's say there's this graph here is extend further to eta equals to 2. So your Vx over V infinity, right? It will converge to somewhere here, a very, very low value around 0.01. Okay, so now if that's the case, right? So let's say we want to get an expression for the boundary layer thickness. Okay, so now so in that case, so we know that eta is equals to y over square root of 4 multiplied to kinematic viscosity and time. All right, so substituting eta equals to 2, and then let's say, right, so since we want to find the boundary layer thickness, right, so we substitute y equals to delta, right, so that you can find out what is the expression for the boundary layer thickness. Okay, so now so now rearranging this one, so what we will obtain is delta, right, 2, so square root of 4, it will be, okay, I'll write it as square root of 4, this one first, so that you can see the changes. All right, so it's actually 2 multiplied to square root of 4 multiplied to square root of kinematic viscosity multiplied to time. So simplifying this one, then you get 4 multiplied to square root of kinematic viscosity and time. Okay, so this is then the equation. All right, this is what I show you how we solve it. So this is then the equation that you can use to solve what is the boundary layer thickness for the case of time-dependent flow when the fluid is suddenly set in motion. Okay, so take note about this equation here. All right. So, all right, I know that this is quite long. Before I discuss the example with you, we'll take a 3 minutes break. But before that, any questions so far? Any questions so far? Anyone?
Actually, I want to ask about
Mm-hmm.
just now the boundary condition that you
Mm-hmm.
defined.
This one?
What is
Okay.
IC?
Initial condition. Initial condition. Initial condition. So the initial condition is where the fluid is at rest, right? So which means at any position of y, when t is smaller than 0, right? So we know that velocity vx is equals to 0. Okay, so that's why, right? So here your phi, right, which is vx over v naught, since vx is 0 at rest, right? So that's why the phi is still equals to 0. Right, so this answer here, it applies to both the boundary condition number 2 and the initial condition. Thanks, Yihong, for asking this. Okay, now anything else? Any further question before we take a break for 3 minutes? Okay, seems like no further question. Now let's take a break for 3 minutes. You'll come back around 10:53. Okay, come back around 10:53. Then we'll discuss about the example. All right, so it's 10:53 now, so we will continue further. All right, so actually the most important part of this part here, time dependent flow, is you need to master how to use this graphical chart here. For the case if we have the flow that is suddenly set in motion. Okay, this is the chart that we are going to use. Now, how we are going to apply it? So let's look at this example here. So, a fluid that is initially at rest on the surface of a flat plate is suddenly set in motion when the plate is being pulled in a positive x direction with a velocity of v naught. So let's say, all right, so if let's say here, okay, so this is the case, like what we have just now. This is the y direction, this is the x direction. So, and then you are being informed that the the plate is set in motion at a velocity of v naught. So you are provided here the kinematic viscosity of the fluid. All right. Okay, it's kinematic viscosity, not viscosity. So kinematic viscosity of the fluid is 3.45 10 to the power negative 4 meters squared per second. And the velocity profile in the dimensionless form is shown in figure 1, which is this one here. This is the velocity profile for a fluid that is suddenly set in motion. Okay, now, so V naught is the velocity of the plate, while Vx is the velocity of fluid, and Y is the thickness of the liquid. Okay, so now you need to find out what is the time taken for the fluid to achieve 50% of the initial velocity of the plate. All right, so 50% of the initial velocity of the plate, right, at the position y. Okay, so at a position y, which is at a distance of 0.5 mm, okay, from the surface of the plate. Now, so what does this 50% of the initial velocity of the plate means here? So the plate is set in motion at a velocity of v naught. All right, so 50% of the velocity of plate, meaning, all right, then it will be the ratio of Vx respect to V naught is equals to 50%, or if we express it in fraction, then it will be equals to 0.5. Okay, now to solve for the time, right? To solve for this time here, if you recall back, right? So we know that the y-axis is Vx over V naught. All right, so Vx over V naught is equals to 0.5, right? And they want to find out at the position y equals to 5, see here, 0.5 mm, right? At a position 0.5 mm from the plate, okay? So what would be the time? Okay, so then, okay, this is eta, right? So eta is equals to y divided by 4 multiplied to kinematic viscosity and time. Okay, so this is what we are looking for. Time is what we're looking for. And for y, all right, so imagine is at a position 0.5 mm. Okay, so what we'll need to do then it would be, okay, so when at a position 0.5 mm from the surface, and find out the time when the velocity is 50% of the initial. Okay, so if you, okay, let me draw it on the line. Okay, so you can trace it here, 0.5. When Vx over V naught equals to 0.5, okay, so intersect at this curve here, the velocity profile. Okay, so then, so let's say, all right, the eta here that you found out, right, so is equals to 0.48. Okay, if it's 0.48. Okay, substituting it, and then let's substitute also the y value, 0.5, right? 0.5 10 to the power of negative 3 meter, then divided by 4, and kinematic viscosity is 3.45. 3.45 10 to the power of negative 4 meters squared per second, okay, and multiplied to time. Okay, so you can try to do this calculation here. So if you proceed to solve it, then the time taken for the fluid to reach 0.5 of V naught at the position y equals to 0.5 mm, right? So it will be around 7.86 10 to the power negative 4 seconds. So we can see that it's a very, very, very small value, which is usually during the startup process, right? The first few seconds or maybe minutes. Okay, so it's a very small value. Okay, so this is the solution for part A. And now they want you to calculate also what is the boundary layer thickness, all right, at the specific time just now that you solve, right? So now for the boundary layer thickness, so we have tried out this section here, right, to see how they get this equation. So this is the equation that you are going to apply to find out the boundary layer thickness for time-dependent flow. So it's equals to 4 multiplied to square root of the kinematic viscosity and time. All right, so substituting. Okay. Okay. Kinematic viscosity is 3.45 10 to the power of negative 4 meters squared per second. And substituting the time, 7.86 10 to the power of negative 4 second. All right. So showing this, the boundary layer thickness, it would be around 0.00208 meter, or which means it's only around 2.08 mm for the boundary layer thickness. Okay. All right, so for this example on how to apply this graphical chart here to solve for flow suddenly set in motion, is it okay? Any questions so far? Or if it's all good, perhaps then you can have to give a thumbs up. Then I know everyone is still fine. So it's much simpler, right? So when all the solution is actually compiled in this chart here, that you can use it directly to solve for the case of time-dependent flow, finding out what's the time, right, when certain position reach certain velocity, and also the boundary layer thickness. Okay, all right. So that's actually the end of the part on the time-dependent flow. So you can go through the solution is also presented in the slides. So we separate into a few slides so we can go through it later again. Okay. So now we will move to the second part here for today. So although there's actually 3 parts, actually this part here is all about unsteady state heat transfer. All right, just that for this second part here, the difference between these two, okay, so this one, the solution that you are going to see how they get the graphical chart is they solve it using the separation of variables method. So I'll just go through it briefly with you, right? The method, how they reach here. But take note, you do not need to formulate it. No need, okay? It's just for your knowledge, okay? So why there are actually 2 sections here? Because for this one that we are going to discuss for the graphical chart method, right? So we are assuming, so let's say for an unsteady state heat transfer, right? So in x direction, so let's say this is a slab, all right? So at some time t greater than 0, so these 2 surface here, all right, so this 2 surface here, let's say it straight away, all right, at time equals to 0, it straight away reach a temperature T1 and it held constant at temperature T1 throughout the whole unsteady state heat transfer process. Then we are going to use this chart here to solve it, right? So while for this numerical finite difference method, it can apply to this case here. You can apply it to this case here, where the temperature at the surface is equal, it will reach T1 and maintain throughout the process. Or it could also be applied to the case where this surface, right, this surface here, right, this surface here for the slab, at time equals to 0, so let's say this is the environment temperature is TA, but your T1 here, it will not be equals to TA. Okay, it could be that kind of case because of, let's say, there's some resistance to heat transfer, right? So resistant to heat transfer near to the surface. Because if we recall back when we draw the heat transfer profile, right, for convection, it looks something like this. This section here is where you have those velocity boundary layer because your fluid mostly flow in streamlined manner. So then your heat transfer is actually most probably by conduction in this region here. So that's why there's resistance to heat transfer. So for this numerical methods, it applies to both. This one here, this case here that I mentioned just now, if at any time, right, the temperature at the surface, it reach T1 directly. But it also applies to the case where your temperature T1 at time equals to 0 is not equivalent to the environment temperature. Okay, so this is how you can apply it, the example that we are going to see today. All right, so let's look at the first one here first, how we are going to use the graphical method. Okay, now again, all right, so when it's unsteady state heat transfer, right, so which means you can expect you have an expression of the rate of change of temperature respect to time, right, and then it will be proportional to the rate of change of temperature, let's say for the slab just now, in X direction, right? If heat is transferred in X direction, because let's say your environment is at some lower temperature, right? While here, your slab here is at a higher temperature, then the heat will transfer in X direction, right? So, and because this happens within a solid, right? So, which means it's a conduction, heat transfer by conduction. So that's why you can see here, it's written as the second derivative of temperature respect to X direction. Okay, and then since it's conduction, right? So which means we will also be dealing with some terms like the thermal conductivity as well. So how this whole equation is being written? Okay, so take note, you only need to understand the method, but you do not need to know up to a level of how to derive it. Okay, no worries. We are going to solve it using the graphical method. Now, so let's see. Okay, so the equation actually looks like this. Okay, so from the equation of change of temperature, so you can go back and try from what we discussed last week, right? The equation of change of temperature, right? So if you do not have any fluid flow, because we are dealing with the case of a slab, right? So if there's no fluid flow, so on the left hand side, all the Vx, the Vy, and the Vz is equals to 0. So then you're left with this term here you need to retain because it's unsteady state heat transfer. All right, unsteady state heat transfer. So on the right hand side, right, so those viscous dissipation term, we assume it to be 0. And since heat is only conducted in X direction, right, so that's why you only see this term here, which is actually second derivative of temperature respect to X. Okay, now for this equation, it's written in this form because if it's the case where your thermal conductivity is not constant over a range of temperature being investigated. Now, if the thermal conductivity is constant, then the equation, it will be rewrite in this form here. All right, so is the rate of change of temperature respect to time is equals to alpha. Okay, then so this del operator here and then square, which means it's actually the second derivative of the temperature respect to X. Now, the question is, all right, so then what is alpha? Okay, so if you observe here, right, so if you compare to this equation here, so which means this alpha is actually the thermal conductivity divided by density and then the specific heat capacity. So this term here, we call it the thermal diffusivity. So this is the thermal diffusivity. All right. So now the example that you are going to see later, how they obtain all the solution being compiled in a chart, right? They do it using the separation of variable methods, and we will discuss the example based on, let's say, a heat transfer by conduction in a final slab at unsteady state. All right. So let's say if this is a slab, all right, this is a solid slab, and it has a thickness of 2b. Okay, so now let's see. So this is, let's say we denote it as position y, y, all right, y here is equals to negative b, and the y here is equals to positive b. So initially in this lab here, okay, initially in this lab, right, so let's say time equals to 0, all right, the temperature, the initial temperature at time equals to 0 is T naught. Okay, that's the initial uniform temperature within the slab. Now, suddenly, right, so let's say at time equals to 0, okay, the surface, these two surfaces here at y equals to negative b and positive b is suddenly raised to a temperature T1, right? So for both surfaces is raised to a temperature of T1 and is homogeneous throughout at time t equals to 0 and larger than 0. Okay, then we will need to find what is the expression for the unsteady state heat transfer, right, for the temperature variation in the slab here. So the temperature, it will then vary in position, right, with the position and as well as the time. Okay, now, so to solve using the separation of variables method, right, they introduce three-dimensionless variables again. Okay, the first one here, so you can say that this is actually the data, right? This is theta, where it's equals to T1 minus T divided by T1 minus T naught. So the T1 here, it refers to the temperature at the surface, all right? That's the T1, all right? Whereas this T here, is the one that, let's say if we are going to solve, what is the temperature at some given position Y and at some time T, all right? So divided by T1 minus T naught. This is the initial uniform temperature. Okay, so that's the first dimensionless variable. And next, they also introduce this one, the dimensionless coordinate. So they still use the same symbol, is eta, but now it's y divided by b. All right, so at any position, y divided by the half of the thickness of a slab. And for the dimensionless time is tau, they use tau to represent it, is equals to thermal diffusivity multiplied to time divided by half of the thickness, square of half of the thickness of the slab. Okay, so by introducing these three-dimensionless variable, they will then now rewrite this equation here. Right, they need to rewrite this equation here all in terms of the dimensionless variable. So you see that this term here, okay, hold on. So you see that this term, the temperature, it will then be replaced with theta, right, which is equals to T1 minus T divided by T1 minus T naught. As for this time here, then they substitute it with the dimensionless time, tau, and for the position, all right, so for the position here, it will be substituted with the dimensionless coordinates, which is represented by eta, right? So then the equation, it will be rewritten in this form now. Okay, so same to all the boundary conditions, we will then need to rewrite it in terms of the dimensionless variable. So let's say for the initial condition just now, right? So initial condition, which is time smaller than 0, right? We know that the temperature is constant at T naught. Okay, so this one that I'm discussing. So for the dimensionless time, the equation is, okay, alpha T divided by B squared. Right, so if time is much smaller than 0, which means or equals to 0, then tau, it will be equals to 0, right? And for the dimensionless temperature, T1 minus T. So now it's T naught, right? Divided by T1 minus T naught, and therefore it's equals to 1. All right. So as for boundary condition 1 and 2, it actually refers to this surface here. Okay, when y is equals to negative b and y equals to positive b. Okay, so eta, all right, so for this case, when time is greater than 0, which means tau, it will then be greater than 0, right? Okay, and for eta, which is y divided by half of the thickness of the slab. So depending you are showing which side of the surface, right? It could be positive or negative. Y, it can be equals to plus minus positive b. So that's why your answer is plus minus 1 here for eta. Okay, and then for the dimensionless temperature, right, the formula is T1 minus T, right? And since at any time greater than 0, right? So these two surface here, it will reach T1 directly. So which means that it's T1 minus T1 divided by T1 minus T naught. So it's equals to 0, because here it will then be equals to 0, right? Okay. Now, then how they propose to solve this one here, separation of variable methods. So again, now they postulate, all right? So this is how some of the mathematician, right? They try to solve very complicated cases. They will postulate a solution to it first. And let's say, okay, let's say this solution here, the dimensionless temperature, right? T1 minus T naught, minus T divided by T1 minus T naught is a function, the solution to it is a function of eta. So F, a function of eta, and G, which is a function of dimensionless time. Okay, so now it's actually quite a long solution. Okay, so now if they substitute, so let's say they solve this one here, all right? So this is, let's say this is the solution, right? Let's say this is a solution, and they will need to substitute it here. So now let's say we solve for the first derivative of theta respect to time, right? So it's only this part here that is affected, right? So then the function of eta is still a constant. Then here it will be written as the first derivative of g respect to time. Okay, now then we'll need to get an expression also, let's say for the first derivative, because here eventually is second derivative, right? So we'll start with the first derivative of theta respect to eta first. Then you should get the g, right? The function of g, then multiplied to first derivative of function of f respect to eta, right? Then solving the second derivative. So solving the second derivative, which means it will still be g, the function of g multiplied to second derivative of f respect to eta, all right? So now that's how, right? So if we substitute it, so function of eta multiplied to this one equals to, on the right hand side is g, okay, then second derivative of s with respect to eta. Okay, so it will look like this, and then if you rearrange it, that's what you see now. Because here, if you look at here, you have eta here and eta here. Well, the variable tau, right, the dimensionless time is here. So we'll need to rearrange the variable so that on the next few steps when they solve it, right, they can do the integration. So you can see now the g is rearranged to here and the f is rearranged to here anymore. Okay, now so from now onwards, right, so uh, it's just an introduction, okay, so it's very tough to solve it now. So to solve the f and g further, right, so they will need to propose another solution to it again, which they have do a lot of trial, and eventually they have decided that negative c squared, so if they assume both f and g is equals to c negative c squared, the solution would be the most tidy one. All right, so that's why you can see here. All right, so they equate, they are actually equating this part. They each of this, okay, hold on, each of this they are assuming that it will be equals to negative c squared. All right, so with this equal to this, right, so then 1 over g, okay, first derivative of g with respect to tau equals to negative c squared. So rearranging this, okay, so you get negative c squared multiplied to g. So you do the same with this one, and then to solve these two equations here, it has to go through a series of algebra and yeah, a lot of things, right? So eventually, for the dimensionless temperature, right, the solution to it is actually an infinite series, right? So that's why we can't actually solve it by hand, right? You may need some computational power to help you to solve this one, okay? And with this, okay, so the whole solution to this one, right, it's being compiled into an example here for the case of unsteady state heat conduction in a slab with a finite thickness of 2b. All right, So with this one here, now take note, for this side, right, if we are referring to the dimensionless temperature for the center of slab, then we'll look at this axis here. Okay, well, if let's say if we are going to solve for the temperature at the surface of the slab, right, then we will follow this section here. Okay, while on the x-axis you can see this is the dimensionless position eta, right? This one is actually the dimensionless temperature tau. Okay, now so you can see, right, at tau, let's say equals to 0.1, so it's still a very small value of time after 0. Let's say at a small value of time after 0, so the temperature has actually at least penetrated slightly into the slab. Well, at the center of the slab, right, so when tau is equals to 1, so let's say almost towards the end of the unsteady state heating process, so the dimensionless temperature, it will almost approach. So here tau almost approach 1, which means you can expect here the temperature at the center of the slab, it has also reached T1, the same as the temperature at the surface. Okay, all right, so 90% completion, all right, for the heating. Okay, now before I go further, right, any questions so far, everyone? Any question? Any questions so far? So the important part is actually we'll need to know how to use those graphical chart to solve for unsteady state heat transfer. Okay, now if no question, I think let's cover this example first. It's a very simple short example, so then after this we will take just a short break. All right, so now for this one, okay, let's go through the question. So a slab with 1.9 meter thick is at an initial uniform temperature of T0. Okay, so let's see at times smaller than 0, the temperature is held at T0. Okay, T0, which is also equals to 300 Kelvin. So now, let's say the two sides of the slab are subjected to a temperature of T1. All right, so here along these two surface here, so at some time equals to 0 and greater than 0, T1 is equals to 533.2 Kelvin, right, for both surface. 533.2 Kelvin. So after a certain time t, it was found that the temperature at the center of the slab, so let's say at any position here at the center of the slab, so is equals to 400 Kelvin. All right, so which means this is at a position of y equals to 0, right? So now this is a slab with a thickness of 2b. So here is negative b, and this position here is y equals to positive b. So which means at the center here, it would be equals to 0. Okay. So now the temperature profile for unsteady state heat conduction for slab of infinite thickness of 2b is given in this figure here. So this would be the chart that we are going to use. You need to find out what is the time taken to achieve a temperature of 400 Kelvin at the center of the slab when y is equals to 0. If it's given, the thermal diffusivity, right? The thermal diffusivity is equals to 1.5, 10 to the power of negative 4 meters squared per second. All right. So now to solve this, so think what we are solving for the time taken for the center of the slab to reach this temperature here. Okay. So then for the center of the slab, right? So now we know all the temperature data, right, for the center of slab here. So which means we can actually find out what is the value here, right? So it mentions the center when y is equals to 0, temperature is 400 Kelvin, but we are looking for the time, all right? So then let's substitute the value, okay? So it would be 400, T0 is 300 Kelvin, okay? So then divided by 400, wait, T1, right? T1 is the surface temperature. So it's 533.2. 533.2 minus 300. All right, so you can see, right? It's a dimensionless variable, right? It's a dimensionless variable. So showing this, the dimensionless temperature here, let me check what's the answer. So it's equals to 0.43. Okay, it's equals to 0.43. Okay, now then if we know that it's somewhere around 0.43 here, okay, so if this is 0.5, all right, okay, I'll use another color to indicate it. So let's say if this is 0.5, then maybe 0.43 is somewhere here, right? So let's say here is around 0.43. But then where should we refer for the x-axis, right? So the x-axis here is the dimensionless coordinate, right? So if we are showing for the time taken for the temperature at the center of the slab to reach 400 Kelvin, then which means y is equal to 0, right? So here that I mentioned, right? So it's 0 divided by half of the thickness of the slab, right? So it's still equals to 0. So which means we'll be reading it along this line, right? Along this axis here. Now, and if you look at all this curve, this one, right? I just take this as an example. So each of this curve here, it represents different dimensionless time, right? Dimensionless time, which is represented by tau, right? So which is alpha multiplied to t divided by b squared. Okay, so now, yeah, we don't have any tau curve actually pass through this point here, right? So unfortunately, then you have to uh, construct your imaginary curve, all right? So you now, if let's say here this is 0.4, the dimensionless time here, tau is equals to 0.4, and for this curve here is where the tau is equals to 0.2. So let's say, which means somewhere between these two, right? So half of it. So let's say if we assume half of it, you have a curve here, the tau will be equals to 0.3. Okay, if let's say if it's 0.3. Now, which mean, all right, so for this one, this curve here, all right, so okay, let me write it down. So when the dimensionless temperature is equal to 0.43, and at the center of the slab, which is eta equals to 0, our dimensionless temperature, okay, that we can found from this chart, let's say is around 0.3. Let's say I assume around 0.33, around 0.33. Okay, so this, let's say you have an imaginary curve here, which is tau equals to 0.3, and along here is 0.35, right? So somewhere for this one, right, which intersect with dimensionless temperature of 0.43, okay, is around 0.33. Okay, then we will substitute all the values, okay, or you can also rearrange it if you want to. Okay, we are solving for time, right? So it will be 0.33 multiplied to b squared divided by alpha. Okay, so what is half of the thickness of the slab? Let's see here. So the slab, it has a thickness of 1.9 meter. Okay, 1.9 meter. So half of it, all right, so you get 1.9 divided by 2. We'll need to square it. And then the thermal diffusivity, okay, 1.5, 10 to the power of negative 4 meters square per second. All right, so solving this, so the time taken for the center of the slab to reach 400 Kelvin for this unsteady state heat transfer, right? So it will be around 1985.5 seconds, or equals to 33.1 minutes. Okay, right? So this is an example how we can solve for the case when we are dealing with unsteady state heat conduction in a semi-infinite, in a slab, all right, with a thickness of 2b. Okay, so any questions so far, everyone? Or if it's all good, then perhaps you can show a thumbs up so I know that you are still fine with following the topic so far. Okay, thank you. Thank you. All right. So it's 11:27 now. Let's take a 3 minutes break. All right, before we start with the last part of our lecture today. Okay, let's take a 3 minutes break. You can come back at 11:31 a.m. a.m. Not p.m. All right. So and I will share the camps code in the chat area. Yeah. Okay. Uh, let me open the camps. So everyone, please check the camp passcode given in the chat area. Yeah? So you have 10 minutes from now uh to key in your attendance. So far, there are only 9 students that taken the attendance. How about others? So please make sure you log into your camps, the app, and update your attendance. Yeah. Okay, 14 students have taken attendance. I think one more student haven't taken the attendance yet. So you still have around 7 more minutes. Okay, all right. So I'll remind you all again if let's say if anyone haven't taken the attendance yet. Yeah. All right. So now 11:31 already. Okay. All right. So, okay. Now, why are you learning about the steady state heat transfer? So, this type of time-dependent heat transfer process, right, it will occurs quite often in the process, let's say, heating and cooling, right? The heating and the cooling process for some foods or some other things. All right. So then if you understand the theory about the steady state heat transfer, right? So let's say if it's a case, let's say if you are designing some whether a material, right, in some different geometry, you want to know which geometry will actually have more effective heat transfer. All right, the rate of heat transfer in at unsteady state will be more effective. Let's say you have cylindrical shape. Let's say for the sausage, let's say, or you are preparing some food material. All right, so let's say for yogurt, sometimes you may find uh, those fruit particles, right? So then what shape is actually the best? Because for yogurt, when we need to manufacture it, it has to go through a heat treatment process to ensure everything is those bacteria is being killed. either pasteurization or UHT, ultra high temperature. Then how do we know what's the shape of the fruit, the geometry of the fruit particles, right? So would be the best. Is it in cylindrical shape, or is it in the square shape, or is it in a granular shape, right? So this is where, right, then we can actually apply the unsteady heat transfer to find out, right? So because if we want to kill the bacteria, so we'll need to know at least the center part here, it will reach certain temperature, right? What's the temperature, and for certain duration. When they want to achieve pasteurization, there are some protocol for it. Like the temperature, it has to hold around 70. I can't remember the range, but it's around 70 to maybe 80 something, right? For at least a few, maybe 30 or 15 to 30 seconds. So then we can use this concept here, the rate of change of temperature respect to time, right? For the center of the slab, right? And then with the tau here equals to some duration here, right? So will it reach the temperature, let's say the pasteurized temperature, let's say T equals to maybe 72. Yeah, I think it's 72 degrees Celsius, right? So this is where say heat transfer, then you can apply it for the analysis. Okay, now, so we'll look at the last part. The last part is actually quite extensive. I think I may be only with the time now. I left with around 20 more minutes, right? And I think only 15 minutes because I need to reserve 5 minutes to tell you about the scope of your test on week 12, right? So I'll only go through the theoretical part for today, right? The theoretical part, then the example. So this one here, you may take it as an extra example, right? That in your lecture note, because in the tutorial question, we have another unsteady heat transfer question. So we'll use that as the discussion, right, for the example. So now I'll only cover the theoretical part, yeah? Okay, now, when do we apply the numerical finite difference method for unsteady state heat transfer? So it's mentioned here. So what we solved previously for the unsteady state heat transfer, right? For the case if you have conduction through slab with a finite thickness, and if the boundary condition are constant at T1 with time. Okay, so what it means here just now, right? Here at any time greater than 0, it will hold constant at T1 all the way. But if the boundary condition, so let's say at time equals to 0, so it's still held at some value T, while the environment is at TA, then only when time is greater than 0, right, the temperature at the surface of the slab, it will reach, right? So this T1 here, it will reach a temperature which is equivalent to environmental temperature, right? So for this kind of time-dependent heat transfer, then we will definitely use the numerical finite difference method to solve it. Okay, all right. It can also be applied to this case here. So which is the example in the lecture notes that if you go through it, it is for this kind of case if T1 here is equals to environment temperature. Okay. Now, so how the numerical finite difference method is being applied, yeah? So now let's say if there's a slab right here, let's say this slab looks like this. Okay, usually in the case of say heat transfer solving by the numerical finite difference method, then we will divide the slab into equivalent section. Okay, we'll divide it into equivalent section that you can see here. And then for the center of each of the section, right? So we will then assign nodes to it. So let's say this is node number 1, number 2, 3, 4, 5, and 6, for example. So then each section here, so you can look at it as if it's like this. The section here, it actually refers to this one, each of this section here, right? This is one this is one section. Okay, all right. Then here we have another section. So example like this. Okay, so divide them into equal section, and then for the center of each section here, we will put a note on it, and then we will derive the equation. Okay, we need to derive an expression, right, to describe what is the temperature at this point here at some given time T. All right, so this is how we are going to apply the finite difference method. So, and then each of this section here, which means it, let's say it will divide to equal section with thickness of delta x. All right, and then and for this method here, we will also work with time increment. So let's say we want to check, okay, so what is the temperature profile for this unsteady state conduction, right? For let's say 6 hours. Then we will need to divide it into several time increments so that we can analyze how the, so it will look something like this. Okay, how should I draw it? Let me, okay, it will look something like this. So, I think it's easier to show you this one. So, okay, hold on, yeah. This one here. So let's say the slab, right? Initially, we know that the temperature is at T equals to 0 is constant at temperature, let's say 100 degrees Celsius. Okay, so then at the third time increment, so now let's say this would most probably the case your environment temperature is at a very low temperature, it's a cold fluid. All right, so that's why you can see as the third time increment, right? So the surface temperature T1 here, so this is node number 1. All right, so T1 here, it has reached 0. So most probably your environment temperature is also 0. So at the third time increment, right? So the temperature will be this one here. Okay, and then at eventually around 6 time increment, it will further drop to this temperature profile here. Right, so it will varies. It will varies like this. Okay, for unsteady state heat transfer. Now, so how are we going to assign the formulas, right? So to describe the temperature or for each of this node here. All right. So now let's see. Let me see here. Okay, and for each of the node, how you can assign it. So let's see this one here. Yep, we are going to describe it as the first node, and this one 2, and then for the center of the slab, right, usually we'll put it as N, and the final node you can denote it as F. Okay, and the one before it, usually you can denote it as F1 minus 1, right? The one which is next to the center of the center section, right? Okay, because this is Tn, right? And then this node here, you can describe it as node n plus 1, while on the left side of the node n, right, you can describe it as n minus 1. Okay, now, so now let's say if we are going to, we will try to obtain the expression for this one. Let me see. Okay, let me see what happens here. Okay. Okay, yeah. So let's say if we are going to get an expression for what is the temperature here at a later time, right? So how we denote it? So the temperature at node N, the center of the slab, at a later time, then it will be denoted as, so time, this is original time T, right? Plus delta T. So at a new time. So that's the symbol that they are using, right? So the temperature at node N at a new time, right? T plus delta T. So how are we going to get an expression? So if you recall back for heat transfer, right? So the heat balance equation is such that the rate of heat transfer in, so you can understand it as, so we have the rate of heat transfer into this node, right? And at the same time, you have rate of heat transfer out of the node. So if it's the steady state, usually we will assume this would be 0, right? Okay, but now this is an unsteady state process, so which means there will be an accumulation term. Okay, accumulation term. So that's why if you look at here for the rate of heat transfer in, right? So how we are going to express it? So for rate of heat transfer in, so for heat transfer by conduction is Ka multiplied to dt dx, right? So and as for the area, yeah, I think we can just express as area. So this is the change in temperature. This is the thickness of the slab. So for this thickness here, for each section, you have equivalent thickness. So we can express it as delta x. All right. So now, okay, the rate of heat transfer into this node here, right? So then it will be, okay, so it will be K multiplied to A divided by delta X, right? So this is the rate of heat transfer in. And as for the temperature difference, so it's actually heat is transfer. Okay, let me correct it, the arrow, so that you can see. Okay, so the rate of heat transfer, so it's from this section here, right? So center of this section here into this point, and then heat is transferred out to this point here. All right, so that's why the change in temperature is expressed as temperature at node n minus 1 at original time t, all right? Yeah, minus the temperature at node n at original time t. Okay, as for the rate of heat transfer out, so it will be still Ka divided by delta X. So from the heat transfer from node N, right? So that's why it's temperature at node N at original time T minus the temperature at node N plus 1 at original time T. Okay, so the rate of heat transfer in minus the rate of heat transfer out, then is equals to the rate of accumulation, right? So for rate of accumulation, if you recall back, is let me think, density multiplied to specific capacity and the volume. So for the volume, then it's expressed as area multiplied to the thickness. Okay, and this divided by time because it's raw Cp multiplied to volume, then rate of temperature, change of temperature respect to time. So that's why here you can see it's divided by the time increment. And as for the temperature difference, it's actually expressed as what is the temperature at node n at a later time. So okay, let me use another color. So that's why it's T plus delta T, all right? And minus the temperature at node n at original time T, okay? So this is how they obtain this equation here. Now, then for this expression of temperature, the equation, right, to find out what is the temperature here at the center of slab, Tn, at a later time, right? So if we rearrange the whole equation, it will look like this, all right? So the temperature at node n at some later time t plus delta t is equals to this whole chunk here, all right? Where the m, right, is being simplified already. The m here that is being simplified is actually equals to delta x squared. Okay, the thickness of the slab, okay, divided by, so where the alpha here is the thermal diffusivity, and then this delta T is the time increment. Okay, all right. So good news is you are not required to derive this. No need. For this topic is all about analysis only, so no need to formulate. That is for your knowledge. All right. So how they actually obtain this one here. Okay. So any questions so far? Anyone? Any question on how they get this equation here? So if no, then I'll proceed to this one. Yeah. Now there's a condition, right? So for using the finite difference method, right? So the first one here, we'll need to know what is the temperature distribution at the initial time. And then you need to select the appropriate delta X, the size of the slab. And for the M value, right, or the delta T, you have to make sure that it will be greater, always greater, or at least equals to 2. Because if it's less than 2, it will violate the second law of thermodynamics, right? So, and usually when we talk about the finest difference method or the numerical method, then the smaller, oops, hold on, yeah. Okay. So usually when we deal with numerical methods, which mean the smaller the value of the slab thickness, right, and the smaller the value of the time increment, when you have more nodes, all right, and you do it for more iteration, then the calculation, the accuracy will increase, right? However, the downside is the cost, it will be very high. One thing is time, right? The time consumption, and also if you're using even for a computer, it will cost some computational power as well. All right. So now you can also try, all right, so how they get this expression here, let's say for finding out what is the temperature at node T1, right? At node T1 at time, let's say time plus at a later time, right? So we know that here, so the heat transfer into the node T1 here is by convection, right? So let's say the environment is at TA. So that's why you can see is convective heat transfer coefficient multiplied to the area, then temperature of the environment at original time T minus the temperature at node 1 at the current time T, all right, at the original time T. So that minus the, okay, I should draw like this. Okay, so minus the heat transfer to this node here, right, at node T2, right, at time T. Okay, so that's the heat transfer out by conduction. So now it's written in conduction already. Ka divided by delta X. So the temperature at node 1 at original time T minus the temperature at node 2 at original time T. So then for the accumulation here, right, so again, you can see it's the raw CP multiplied to the volume. Now, for this case, when we deal with the first node, we are only analyzing half of the slab. Okay, so that's why you can see is area multiplied half of the thickness of delta X. All right, and for the temperature here, it can actually be simplified and rewritten actually as temperature at 0.1 at some later time minus the temperature at 0.1 at the original time, right? So we can actually substitute it in this to simplify the calculation later, right? Instead of expressing it as the temperature here, right? So we will simplify it in this form, okay? So this is the rate of accumulation term, all right? So again, if you spend some time to do the rearrangement, so this would be the equation to solve for the temperature at node 1 at some T plus delta T. And it only applies to this case here, where the n is equal to this and when the m is equal or greater than 2n plus 2. Okay, now then the last one we also have here. So let's say at this Tn, all right, and if it's the case where here we have insulation, so which means it's an insulated boundary, right, at the position n equals to f, right, is an insulated boundary. So if it's the case where insulated boundary, okay, so you can try to do the derivation, but here is a simplified form of the equation, right? So usually for TF at some temperature, at some time later, right? So we can apply this equation for the calculation. Okay, now it looks a bit very tedious, right? There are a lot of things that need to calculate. Actually, if let's say, all right, if let's say the n value is equals to 2, we can apply the method which is called the simplified split method, right? Where the case m is equals to 2. So this m value here, if you recall back, okay, what is the m value? This one. Okay, so m is equals to 1, yeah, is equals to delta x squared divided by alpha t. So if this value is equals to 2, the case just now for this one, the temperature at the center of slab at some later time, right, it will then be simplified into this form here. Okay, let's look at the equation just now. Okay, this one. So just imagine if this value goes to 2 and this value goes to 2, so which means this part here, it will be equals to 0, right? So eventually, all right, the temperature at node n at some later time t plus delta t is equals to half of the temperature of this one, Tn plus 1 at position, this one, plus Tn minus 1 at time t. So meaning if you look at it, right, it's as if the sum, all right, the half of the sum of this two here, the temperature at these two nodes here. If let's say m is equals to 2. So if you are applying the simplified Smith method, right, to calculate the temperature at the center of the slab, so this is the formula that we can use it. All right. So there are further procedure here that I'll need to describe, but I think there are a lot of things that we covered today already. So I will stop here first, All right, and then we will continue tomorrow, right, on the theoretical part on how to solve the as I said, heat transfer using numerical method and the simplified Smith method, right? So this is only one of it, because later for solving this T1 here, so what is the simplified equation? And for solving TF, what is the simplified equation? So we'll discuss it tomorrow. Okay, all right, we'll discuss this tomorrow. Okay. Now, this example, you can take it as an extra example that you can go through it yourself when you have time here. All right. Hold on. I think there's a message in the chat area. Okay. Yeah. So, okay. Allow me to generate the passcode again. If anyone missed it just now. Yes, there should be 15 students. Okay, so the new passcode for until 12 p.m. is in the chat area. Okay, now about your test. So I have posted this announcement here on week 12, right, under week 12. So your test would be on Thursday. So we'll use the lab time, right? So since we do not have any lab session anymore, so please gather at 2 p.m. All right, so the paper will be around one hour. I haven't set the question yet, so I'm not sure there will be how many questions. At least maybe two to three questions. All right. So because here if you look at here your test, right? Okay, it's only 10 marks and it should cover the third learning outcome. So third learning outcome, which is here about formulate temperature and velocity profile for fluid flow through various geometry. Right, so we'll need to do it on week 12. So your scope, it would be anything that we covered from week 1 to week 9. So I couldn't say that this will only focus on which week, even if it's just for formulation of temperature and velocity profile, because you can see some of the things that we discuss are actually interrelated, right? But you can, let me double check. But you can put more focus, right? If you recall back, week 3, so for formulation of velocity profile, okay, we have covered it on week 3. That is using the shell momentum balance method. All right, so you can put more focus on this one here. And then for velocity profile, we also learn about another method, which is on what we learned on week 7, which is the Navier-Stokes equation. Okay, that's for velocity profile. Okay, as for the temperature profile, we covered on 2 different weeks as well. That would be on week, let me check, which week? Okay, yep, week 5, all right? Week 5, which we use the shell balance method to derive the temperature profile. And then another one, which is on last week, right? Yep, week 9, which you learn about the equation of change of temperature. So you can give more focus on those learning material that we discussed on this 4 particular weeks. The rest you can just glance through it. The reason I cannot opt out other topic, because for example, when we derive the velocity profile, you need to know what is considered as Newtonian fluid, right? And for what is Newtonian fluid, what is non-Newtonian fluid, and how the equation looks like, the formula looks like, is what we learned in week 2 and also week 1 actually. All right, even for the shell balance method, right, the basic of it, the conduction equation, how it looks like, how you write it, is from week 4. Okay, so that's why I say you still need to go through it, right? At least you have an idea how the equation looks like, right? But you can put more focus on this 4 week here, especially when we discuss about the formulation of temperature profile. Okay, so okay, so one thing is I will highlight, I think definitely this one, there would be one question on shell momentum balance method. Okay, so please make sure you master this part. So you can start to do a revision on this. If you have any question, right, you can start to ask me from this week onwards. Okay, master the shell balance momentum method. So this one will definitely, so I'll give you a clue now. This topic will definitely be tested. Okay, so I haven't set the question paper yet. So I think a week before week 12, I will inform you how many questions. It will be a minimum of 2 questions, one on temperature profile, one on velocity profile. Okay, yes, any question?
Want to ask is like when you say cell momentum balance
Uh-huh.
method, is it
Okay.
specifically for velocity profile or it could
Yeah,
also
yeah.
be
So for velocity profile, I think definitely you have one question, how to solve it using shell momentum balance method. So you can start to do a very good revision on this. Now, I would encourage you, although I mentioned that this will definitely be tested, please also go through this method here, because the reason why, most probably in your question paper, right, in appendix, I will also provide you the Navier-Stokes equation. In case, worst case, if you really don't know how to start with the shell momentum balance method, I will allow you to proceed with the Navier-Stokes equation. But take note that because Navier-Stokes equation, it start from a simplified part, right? So you lose some mark on the part where you derive, formulate all the terms from scratch at the start. So you can expect that you may lost half of the percentage of the total mark here. Okay, so that's why, although I mentioned that shell momentum balance will be tested, please also go through the Navier-Stokes equation method. In case if you can't do the shell momentum balance, you have this as a backup. Okay, so this is something that I could help you. Right, so please study both. Okay, so any questions so far? Any questions so far? We have only 1 more minute. Now I'll need to leave for another class really. Okay. Now, so this is posted on week 12. And another thing is the TS evaluation, right? The window is started already. So if you have time, right, please take some time to complete the evaluation. So just a reminder, 5 is like A for your test. 4 is just B, and 3 is actually fail already. You just pass, your lecturer just pass for teaching only 50%. 3 is just passing, 2 and 1 is fail already. Okay, so I would like to collect your feedback for this module also, like how's the module, the curriculum, how it's being conducted, and about my teaching. Right, so if you have anything that you like to, how to say, uh, commendable, in fact, something that is good, you can also mention about it as well, or anything that I could improve further, or the modules we can improve further, you can also mention here. All right, so I'll post this link in Telegram later so that you all can drop your feedback. All right, so yep, I'll post this link in the Telegram, or you can screenshot it now also. Okay, for the QR code. All right, so that's all for class today. Thank you very much. And then we'll discuss further on the numerical methods tomorrow, 4 to 6. Okay. All right. So if there's no further question, then that's all of our class today. Thank you very much. I'll see you tomorrow. And very sorry, I have to leave already. Yeah. So I will post the same thing, the recording of that's the pre-recorded lecture video. All right. So in case you want to refer back any section, you can refer to it. All right. So I have to leave first. So sorry. Thank you, everyone. All right. So and remember to complete